All right, ladies and gents, the last thing that we're going to make sure that we focus on with vectors is this idea of taking two vectors that are pointing in slightly different directions. So like one's pointed at 80 degrees, the other one's pointed at 115 degrees, and finding out what the resultant force would be if these two things are operating together or against each other, just like slightly together, slightly against each other in this case. So looking at this, the first thing that I do is I try to conceptualize the problem. So like if I have a 500 magnitude vector pointed this direction and a 22 magnitude vector pointed this direction, then the resultant vector is probably going to be like still mostly in the direction of the 500, but this one's going to pull it left a little bit because it's pointed to the left, and it's also going to since they're both pointed up, they're going to push together up a little bit. So I would guess that like maybe the resultant vector might be something like that. Like it'll trace up kind of in that direction. In order to do this, what we're going to need to do is break these vectors down. So every vector, we've talked about this already, can be made up of like a horizontal and a vertical component. In fact, that's how we've written most of them to this point. But in real life, you never say, yeah, set off 10 units north and 5 units east. Like, we don't do that. We just like point down a road and say go that way for 3 miles. Almost everything that we do in terms of giving directions has a lot more to do with giving a direction and a distance than it does with breaking something down into its horizontal and vertical components. So, in real life, you're far more likely to end up having these polar things that show a magnitude, 500, and a direction, 80 degrees, than you are to have an x and a y value like we've seen in these other vectors. So, let's break this down. We know that this is going to be made up of some horizontal component and some vertical component. And we can also see the same thing here, some horizontal component, some vertical component, much smaller in both cases. But you can also see that like vertically they're working together. So once I find these two vertical things, I'll add them together to get the final resultant vertical vector. And horizontally they're working against each other. So once I find the two horizontal components, I'm going to take the bigger one and subtract the smaller one from it. There's something cool that will happen in the calculator here that will kind of do this automatically, but you'll see. For the sake of keeping everything straight, let's call the huge vertical component V1 and the horizontal H1, and the small vertical V2 and the small horizontal H2. Okay, so you've already seen this many times, a lot of you, but the idea here is you see a triangle. So if this is 80 degrees right here, 80 degrees, then this becomes a right triangle that we can use trig on to find these missing sides. The sine of 80 degrees would be equal to opposite over hypotenuse, which in this case would be h1 over 500. Or v1. v1's opposite, not h1. Sorry, see? Got to think all the time. v1 over hypotenuse, which is 500. Now, to solve for v1, I could multiply both sides by 500. So I'll end up finding that 500 times the sine of 80 degrees will equal v1. Use your calculator for this moment. So 500 times the sine of 80 degrees is... I'm in radians, aren't I? It came out negative, which surprised me because this seems to be like a positive vertical thing, and that's how I knew I was wrong. There it is, 492.4. So V1 is equal to 492.4. To find H1, the horizontal component, well, that's the adjacent side. So I'll use this exact same formula, 500, but instead, since it would be H1 over 500, I'll use cosine of 80 degrees to find my H1. So that one, H1, gives me 80.8. You may already see what's going to happen here. If the sine corresponds to the vertical and the cosine corresponds to the horizontal, you might recognize that as being exactly the same as the unit circle. You'll remember that sine was always the y component, the vertical, and x was always the horizontal, the cosine. And so these like same correlations here hold true. So I don't really even have to draw out the triangle. I can just know that the exact same thing will be true. If I take that magnitude, 22, and multiply it by the smaller one is 115. Okay, so if I take 22 times the sine of 115 degrees, then I'm going to get my same vertical, but for the other vectors, so v2. And if I take 22 times the cosine of 115, I'm going to get my horizontal vector too. So let's do this real quick. 22 sine of 115. It gives me v2 was 19.9, and then 22 times the cosine of 115, it gives me negative 9.3. And actually, now that I think about it, that makes a ton of sense, because this horizontal is pointed left. It's pointed in the negative direction. So the fact that I got negative 9.3 isn't actually that weird or surprising to me. So now that I know both vertical components, 492.4 and 19.9, and both horizontal components, 80.8 and negative 9.3, combining these is as simple as like the old school adding vectors that you did a long time ago. You just take the x's and add them, you take the y's and you add them, you take the verticals and you add them, you take the horizontals and add them. However you want to think about it, you've already done this many, many times, and you've done it really well and really successfully. So, moving back to what we've got here, and using a sock to erase, because why not? Our final finished big vector, the result of adding these two smaller forces together, a 500 and a 22 magnitude force, is going to be, I'm going to call it V final and H final. So V final will be 492.4 plus the other V, which was 19.9, and the horizontal final will be 80.8 minus 9.3, and again, we're minus because it's negative, and it's negative because it's pointed in the opposite direction, so that all makes a lot of sense. So, doing this addition, 492.4 plus 19.9 gives me 512.3, and the horizontal, I get 80.8 minus 9.3. I get 71.5. So that means that my very final finished vector has components of, horizontal comes first, doesn't it? X and Y. 71.5 and 512.3. Now, this is true, but if the problem asks for a final distance and a final direction, then what I've got to do is I've actually got to plot this out and find like Pythagorean theorem to get distance and direction. But you've done this many times, so I'm actually not that scared for you. All right, I'm going to make a new drawing of this vector. It goes up 512.3, and it goes over 71.5. So draw out your triangle. And because this is the same as that side, 512.3. So 71.5 squared plus 512.3 squared. Gives me a massive number. Take the square root of that number. I got 517.3. And that makes sense. Because if I think about my original forces, if it was 500 plus 22, but they're slightly working against each other, it would be a little bit less than the two of those put together, a little bit less than 522. But since they're mostly working together, it'll still be a little bit more than 500. Rad. So now, last thing I gotta do is find out this angle right here. The way that we've been doing this lately is by saying that since tangent of that angle would be opposite over adjacent, so 512.3 over 71.5, then arctangent is going to be my best friend here. So I'll do arctangent of 512.3 divided by 71.5. I got 82.1 degrees. And what that means, that actually makes sense too. It was originally pointed 80 degrees. It's going to pull it a little bit to the left, so this actually looks really good. So my very final finished distance and direction for where this vector is pointed once you add these two smaller vectors together. The magnitude of this final vector is 517.3, and it's pointed in the direction of 82.1 degrees. Easy peasy.